Question 3 from the Trig booklet, the step 2 booklet. This is a great question because it just allows me to do some more integration, which is always nice. First, I'm going to prove this result here by using x equals a tan theta. So of course, x squared is a squared tan squared theta, and dx is a sec squared theta, d theta. I can just put both of those results in here, and you'll end up with this here. If you factorize out the a squared from the denominator there, you'll see that 1 plus tan squared is, of course, just sec squared. So this object and this object will cancel. 1 over a squared times a is 1 over a. Remember, you're not integrating with respect to a here. You're integrating with respect to theta. So that's just 1 over a times theta when you integrate it, plus c, of course. And then theta, if you rearrange this, is tan theta is x over a. So theta is arctan over x over a. And you just put that in, and you end up proving the thing that they want you to get. So that was really nice and straightforward. Let's move on to the next bit. To do these sorts of integrals, when you have a trig integral and you've just got a random cos x sitting on the numerator, key substitution to always bear in mind that might work is just u equals sine x. And the reason that might work is because when you differentiate, you get du equals cos x dx. And then you can just divide both sides by cos, and that'll cancel out this cos for you. And it doesn't always work, but in this case it works beautifully because the coses cancel, and you just end up with 1 plus u squared du. Just there, which is fantastic because that's the integral that we just evaluated with a being 1. So this just goes to 1 over 1, which is 1, arctan of x over 1, which is just x. This is arctan of u, actually, I should say, isn't it? Because it's in the u world. Between 1 and 0, I should mention these bounds, of course, changed. Sine of a half pi is 1, and sine of 0 is 0. So, yeah, arctan of 1 is pi over 4, and arctan of 0 is 0. So that's just going to be our answer right there. Next, we're going to use this substitution to evaluate this. Now, this is really interesting because t equals tan a half x is known as a T-substitution or a Weierstrass substitution. You usually use it when you have integrals that are in the x world and you put them into the t, but this is the other way around, which is really interesting. And it makes it much messier, but okay, whatever. Dt equals sec squared a half x times a half, I guess, because of the half coming out here. Sec squared is 1 plus tan squared, as we saw on the previous slide. And so now I can just shove this dt result all into here. And now all of these t's can become tan over half x's, just like this. And now what I'm going to do is I'm going to pull this half out to the front. By the way, sorry, the limits as well. So when t is 1, you get 1 is tan a half x. So arctan of 1 is a half x, which is pi over 4 equals a half x. Double everything to get pi over 2. And when t is 0, arctan of 0 is 0, so x will be 0. So that's just where those limits came from. Now I'm going to pull the half out to the front and multiply 1 minus tan squared times 1 plus tan squared, which makes it's a difference of 2 squares, of course, 1 minus tan to the 4. Now, because I've got the half here, and because the limits match up with what was originally here, what I'm going to try and do to show that this is a half I is just essentially show that this integral here is the same as this integral here. In other words, like I said, because the limits already match, I just need to show that cos over 1 plus sine squared is the same thing as this, one way or another. And I did this in a very messy way. There's probably much nicer ways to do it. Firstly, I just, for shorthand, wrote sine s is sine x over 2, and c is cos x over 2. And I just shoved those in like this. And then I just sort of put all this together. So this is cos to the 4 over cos to the 4, so you can take those away once you make them equivalent. And likewise, times this by cos to the 4 over cos to the 4, this by cos squared over cos squared. You can put all those together. Now this cos to the 4 cancels with this cos to the 4, which is fantastic. And also, this is a difference to 2 squares, which you can factorize. And finally, although this takes a little while to spot, you can break this 6 into a 4 and a 2. Now, why would you want to do that? Well, there's a couple of reasons you'd want to do that. Remember, we S and C refer to these two things. Hopefully, we just know the double angle results off the top of our head. But the key thing about the double angle results, of course, is it's not just referring to the 2x and x rearrangements. It's the double angle formula. It's referring to anything where this is double that. So you can replace this with an x here, and x over 2 is over here. But this is just our SC business that we've got going on before. So we can say 2SC is just sine of x. So therefore, if we square both sides here, we'll get 4s squared c squared is equal to sine squared of x. So this is sine squared of x right there, which is fantastic because cos squared plus sine squared is just 1 no matter what. So that's going to go away. Doesn't matter what the arguments are in here. That's going to go away. Cos squared minus sine squared. Now, that should feel familiar. That's the other double angle that I'm going to use here. Again, halve all these x's to get this. And this is our c, this is our s. And so I can replace this business here with just cos x. So okay, to round up, that's going to go away because it's a 1. That's going to become cos x. That's going to become sine x. And now what happened to this 2c squared s squared? You know, it's very convenient that I removed that from the 4 just to give me the correct sign here. or sine of x here. But it's even better than that, because if you just rewrite these in a new order a little bit, you get this statement, which actually just factorizes perfectly to c squared plus s squared all squared, right? Which is fantastic because, as mentioned before, c squared plus s squared is just 1, because it's sine squared plus cos squared. 1 squared is just 1, and you end up with this here, which is exactly what I was trying to get to. So therefore, this is equal to a half I, and we've shown the result as we were asked to do. So pretty tricky algebra there, but as long as you just sort of stuck through it, there are probably other ways to do it as well that were nicer, but yeah, that's nice. I mean, key thing here is knowing the malleability of these results here, I think, is the key idea for this question, and being able to rearrange these to be always looking for the c squared minus s squared, c squared plus s squared, and the c squared s squared, looking for those kind of 3 results and trying to force them into the business, so that you can then force more of them in, and getting the answer, I think, is the way to do it. Okay, cool. Next question is the last question of this, which is just classic step stuff. Just evaluate that integral using the stuff we've done before. Now, of course, all this is going to look basically exactly the same, because this is the same integral that we just did, but with a 14 here instead of a 6 here. So I'm going to do this very quickly. Everything is identical. I've just done the same substitution, put it in, put all that in. I'm going to do exactly the same thing here to break down all my c's and my s's. So I haven't written it here, but c is still cos x over 2 and s is still sine x over 2. You put it all in, you get the same thing on top. Now, you don't quite get the same thing on bottom, because before we had 4 s squared c squareds left over. But now, of course, if we're going to put 2 of them over here to make this factorize really well, we're going to have 12 lots of them left over. Now, bear in mind, of course, that we said before, 4c squared s squared was just sine squared of x, right? So therefore, 12 of them is going to be 3 sine squared of x. And this here factorizes still to just s squared plus c squared all squared, which is just 1 squared. So that's just going to be the 1 here. So all of this work has worked out just exactly the same, except there's a random 3 here when we used to just have a 1. So, okay, all we have to do is figure out whether this is still integrable or not. And now we just need to think back. Well, how did we do this one? Well, we did it with the substitution u equals cos x. So I think that's exactly what I'm going to do. First, I'm going to factorize out a 3 from the denominator, which will make it 3 into a third plus sine squared. And then I'm going to put that 3 on the bottom, which is essentially a 1/3 on the outside, like this. So that's all I've done there. And now I'm going to use u equals sine x, because that works so well on the first one, and the fact that there's a 1/3 here doesn't feel like it's going to make too much of a difference. Differentiate, of course, throw that in, and the cos x will cancel with the cos x, as it did before. Sine of pi over 2 is 1, so that goes there. Sine of 0 is 0, so that goes there. 1/3 is 1 over root 3 all squared. So now I'm perfectly set up. I've got the result that I can use here. A is acting as 1 over root 3. And this is just going to be 1 over root 3, which is just root 3. Arctan of x over 1 over root 3, which is just root 3x. And put in 1, put in 0. Arctan of root 3 is pi over 3. Arctan of 0 is 0. So we have root 3 times pi over 3 is going to be this. Take away 0 is nothing, and we end up with this as our final answer. Really nice little question. All right, so this is the last question in the trig booklet. It's quite a tough question, I thought. The first thing we're going to do is something quite fun, showing sine of 18 as this thing here. But before we do that, we have to first show that cos theta, or find values for theta such that cos theta was sine 4 theta. So what I thought I'd do is I'd break down sine 4 theta a bit. This is the double angle formula, but as I always say, it's not the 2-angle formula, it's the double angle formula. It refers to this angle always having to double to get there. But you can use whatever you want. So sine 4 theta is therefore 2 sine 2 theta cos 2 theta, which is useful because now we can break this one down into that. And then we can break down cos 2 theta and sine 2 theta into their respective things that we always know that they are. And if I do some expansion out there, we'll get this. First, I've replaced sine squared with 1 minus cos squared, I guess. And now I think I'm going to expand out. And that's our expression for sine 4 theta. So now we're going to set that equal to cos theta. And notice that cos theta runs through all of them. So if cos theta is 0, that will be a solution. Otherwise, we can divide by cos theta and end up with this. And now we can turn our entire equation into a sine equation by writing that there as 1 minus sine squared. So cos theta equals 0 has a couple of solutions, right, in this range. Or does it just have one? Just the 1 of 90, right? But then we can change this cos squared into a 1 minus sine squared and keep going. With some signs, we get this. Some stuff cancels. You get this cubic here. I guess at this point, we just need to try stuff, try and do some factor theorem to find a solution. If you think hard enough, you'll find sine is minus a half. When you're doing sine and cos, half is always the good one to try, of course, because you know that that's a thing that you can work out the value of theta for later. I think a half works because you get a half to the power 3 as an eighth, so that makes a whole 1 here. A half times 4 is 2, so it's 1 minus 2 plus 1, which is indeed 0. So a half works, which means a factor is 2s minus 1 if you just write sine theta as s, I guess. And then, yeah, you can do some polynomial division here if you want, or you can just spot the things. This times this is 8s cubed. Minus 1 times minus 1 is plus 1. And now we want no sine squareds. Currently, we're getting minus 4 sine squared, so we're going to need a plus 2 sine there to make plus 4 sine squared back again. Good, so that's our factorization. We can now look for solutions of this. It doesn't factorize after a little bit of trial and error, so we can just do some formula. By the way, so of course sine theta is a half is also a solution which gives you 30 and 150 in this range. So yeah, let's use the quadratic formula on this. We get this, that makes 20, which is 2 root 5. Divide everything a little bit by 2 there, we get this. Which is, I don't know the values of theta that give me this, but it is very interesting that that looks basically the same as what's up here. So how do I relate this? How am I supposed to know that 18 is going to give me the minus 1 plus root 5 thing without just asserting that, I guess? How am I supposed to know that? Well, what we have to do is go all the way back to the top. So currently what I've got is for this to happen, either this is true, which gives you that, or this is true, which gives you that, or this is true, which gives me things that I'm not sure about yet. But if we go all the way back to the top and think of, is there another way we could try and solve this? Well, cos theta is just sine of 90 minus theta, the very underused trigonometric identity that people don't think about. Certainly, well, I say people, that I don't think about enough and don't use enough. But of course, we can just set that equal to sine 4 theta, and now just say, well, 90 minus theta has just got to equal 4 theta, which gives you theta as 18. Which must just be, because we already know that the only values of theta we're missing come from this one here, this now tells us that sine of 18 must be either minus 1 minus root 5 or minus 1 plus root 5. And it also has to be minus 1 plus root 5 because sine of 18 is positive. So that will be enough to assert this, I think. And now, are we missing any other solutions? Well, sine of theta equals minus 1 minus root 5 is not going to give you a theta value between 0 and 180. So I'm not missing any from there. But I could be missing another minus 1 plus root 5, and of course I am, because if sine of 18 gives you that, then of course 180 minus that, 162, will also give you that. And like I said, because the other one is negative, and because we found all the other solutions from all of the other conditions, I think these 5 things there are going to be the things that we were looking for, and we've shown this thing here, so I think that's all good to go. Part 2 is, I thought, probably the only relatively straightforward bit about this entire question. So yeah, well, firstly, we can replace s with sine x, of course, just to make everything easier. Use the double angle formula again. If you square all of this, you're going to get sine squared of 2x equals 4 sine squared cos squared, which I guess I can just throw straight in there once I replace cos squared with, of course, 1 minus sine squared and do some expanding out maybe. Then I can put it all in. Remember, this 4 is also still sitting over here, which is good. So that's fine. We can just use that. And expand everything out and rearrange, and you eventually end up with this quartic in S. And now I think we just need to use some quadratic formula here, because I couldn't find any things by factor theorem that easily worked. But if you have a quartic like this, quadratic formula just works as long as you arrange it for the thing that's just here and being squared there. So because this is s squared or squared, and this is just s squared, if you want to, you can make a substitution in your head of like s squared equals u. But in any case, the quadratic formula, you can just use s squared here. And if you just run down the maths a little bit here, this is 4 root 5. So we can divide everything by 4, I guess, at some point. Or actually, I think I only did it by 2, just sneakily, because I wanted, after I square rooted both sides to get s, I wanted to root this 16 down to a 4. And if I halved it again, it would be an 8, and that would be just a little bit annoying. So I wanted to root that down. And now we're left at this thing here, which, I'm trying to get it in this form. So how do I do that? Well, I've actually made an entire worksheet on questions like this somewhere for people to do, which is quite fun, of trying to deal with surds inside of surds. Your aim will be to try and write this surd in here, 6 plus minus 2 root 5, as something squared. And if you sit here and think about it for long enough, you find 1 plus root 5 all squared, because when you square this out, you get 1 plus root 5 plus another root 5 will give you 2 root 5. Plus root 5 times root 5 is 5, which added to the 1 makes us 6. And likewise, if you use the minus, all that happens is you get the minus 2 root 5 in here. But now, of course, this root can cancel with this square, sort of. Technically, you should be using mod signs here, but it's not really going to matter when I just have to list out every solution anyway. So our solutions are plus and then plus, or plus then minus, or minus then plus, or minus then minus. And we can have all four of those things. I don't know whether I wrote them out properly. I didn't. I just left it like this. But there will be those four kind of group solutions. Again, worth noting at this point that one of those, specifically the plus minus, sorry, the minus plus case, no, the minus minus case. Yeah, the minus minus case is this one up here. Is sine of 18 equals this. So that suggests that sine of 18 is a solution to this, which is kind of interesting. And I think is actually going to be used for this last part, which I thought was the most tricky part. It says hence. So somehow we have to relate this to what we've just seen. Now, we've just seen that sine of 18 is a solution to this because it's one of the things that we get from here, along with, I presume, some other solutions. So how do we get from this to here, or vice versa? Well, okay, we have a square thing here, we have a square thing here, we don't here, but I guess 1 is just 1 squared. So is there a way to write that in terms of sine? Except not quite, because we've got 4's here, which we don't have in the second one. So let's just take this and divide it by 4. And note that, of course, the solutions to this are the same as they were before, because all I've done is divide by 4. But now is there a way to write, and notice that, 3 alpha, 6 alpha, that seems to match up quite nicely. So a quarter is the only thing that's kind of wrong here. But I guess I could write a quarter as a half squared. And then I could write a half as, well, the most obvious way to write it would be sine 30. Because now we have sine squared of 30. And this is looking a lot like this. And, if 5 alpha was 30, that would make alpha 6, which would make this 18 and that, 36, which is fantastic because we already know that sine of 18 creates this, which is one of the solutions, and so this is all good to go. So alpha is 6 is definitely a solution to this because we started here, we know all the solutions should be the same as they were before, and 5 alpha equals 30 gives alpha equals 6, gives you x was 18 from here, 3 alpha equals x, 3 alpha is 18, and x equals 18 was a solution up here. So that's all consistent, that's all good. So we have one of the solutions. So where do we get another one from? Well, it's because, a half just choosing to be sine 30 was kind of arbitrary. It's just the most obvious one. But you could have chosen sine of 150, right? That would also give you a half, and it would give you a different alpha value. But also, you could make this minus a half, no? Minus a half squared still equals positive a quarter. So actually, we just want to find any values of 5 alpha, I guess, that will give us plus or minus a half. That just coming from here, which just shows that it works. So, okay, sine of 5 alpha plus minus half. So 5 alpha means we're looking between 0 and 450. Okay, well, the half gives us 30 or 150, but the minus a half will give us 210 or 330. And then there's one more in range, which is 390. So let's divide all those by 5, and that's the one that we said we were happy with. Now, what about all 4 of these others? It's only asked us to find one more after the alpha equals 6. So why have I got 4 more? Well, this is where we need to check that the x that we get back, to relate it back to this question, actually gives you solutions that look like this. So if we times all of these by 3, which will give us the x values that, because this will be 3 alpha as x, which will relate it back to here, we get x is all of this. Now we know 18 works because we already discussed that 18 does this because we showed it earlier. Now x equals 90 clearly isn't any of these 4 options. So x equals 90 can be disregarded. Now what about 126, 1098, and 216? I don't know the values of those for sine of those off the top of my head. So how do I know that they're not any of these? Well, the way that I can argue is that if sine of 18 is one of these things, that means that the others must be sort of 18 away, forwards or back, from the origin. So therefore, as we said before, sine of 162 is also this, but also sine of 198 would be some other form of this. It would just be the minus case of this, right? Because you're just going down to the minus value you were before. So it would be the minus case of this one. And guess what? 198 is sitting right here. So I think that one is acceptable because sine of 198 must be this, but just negative, which is one of these things here. So 198 must be okay, which referred back to the alpha as 66 case. And so 6 and 66 will be our two alphas that we'll use. Oh, sorry, I didn't bother writing them down at the end there. But alpha 6 and 66 are going to be our two cases. Really tough question, but thanks for sticking with it if you did, and I'll see you next time.